All right, we want to look at orbital periods using universal gravity. So we noticed that v of an orbit, when we were using the universal gravity equation, it turned out to be the square root of big G, mass of the planet, or let's say Earth, or whatever it was, divided by how far away you are, some distance r above the center of that planet, whatever r you were away. So if we had some planet, you're some total distance r, and here's you making you're orbiting with some speed around the planet, right? And this has some mass of the planet, or whatever object it is you're orbiting. Now, when we want to look at period, if you remember before, we said that period, the velocity of our period is the distance 2 pi times however our orbital distance is, the circumference, divided by the period, or the amount of time it takes to do that. So this was our velocity. So we could put v in over here. And what do we see? We see that 2 pi r over t equals the square root of big G, m of the planet, or whatever you're orbiting, times r. So if we square both sides to get rid of this, we see that it's 4 pi squared r squared over t equals big G, mass of the planet, over r. Oh, this is squared. Okay. So multiplying both sides by t, we get, and multiplying, so we'll cross multiply, the r will go over here, the t will go over there. We have t times big G, mass of the planet, equals 4 pi squared r cubed. And this should be t squared. Now t squared then is equal to 4 pi squared r cubed divided by big G, mass of the planet, or the object you're orbiting. We see that the orbital period t squared goes approximately with r cubed. So the amount of time it takes you to make an orbit increases with the distance away from whatever you're orbiting. Now we have something that we can check this against, and this is called the solar system. So as we look at our planets in the solar system from the sun, every time a planet's a little bit further away from the sun, it takes longer to orbit. The Earth takes 1 year to orbit the sun. Venus takes less than a year. Mercury takes even less. We go out to Mars. Mars is further from the sun than the Earth. And then Mars takes, I think, like a year and a half or 2 years or something. It's a little bit longer than the Earth. And as we keep moving further away, the planets take longer to orbit. So as they get farther away from the sun, the orbital time increases. And this is what this equation tells us. And so we see how orbital periods change with distance. If you want to put something like a satellite into orbit, the farther away you get from the planet, the longer it's going to take to orbit that object. And so this law here, this t squared goes as r cubed. This was actually not discovered by Newton. This is actually one of Kepler's laws of planetary motion. The other one being that planets don't orbit in circles, they orbit in ellipses. That's the first one. And the second Kepler law is that you have to do what's called equal area and equal time. And the third one is that the orbital period squared goes roughly with the distance cubed. So this is the idea of orbits and periods, that we see that there's a relationship between the period, the time it takes to orbit, and the radius cubed. And we can get the actual physical numbers by looking at